Hi, my name is David Bombara, and this is my presentation for the 2020 International Conference on Soft Robotics. My presentation is on compliant and large-strain twisted string actuators using supercoiled polymers. I would like to thank my co-authors as well, Zhang, Stephen Fowzer, and Brennan. My email is dbombara@nevada.unr.edu. Please feel free to email me if you have any questions. I work in the Smart Robotics Laboratory at the University of Nevada, Reno. First, I'll start with an introduction to our work and how it relates to the soft robotics community. In the motivation and contribution section, I'll detail why exactly we are performing this study and how exactly we can help solve the research problem. In the design strategy section, I will discuss our design considerations in proposing a new actuator. I'll also talk about our experimental setup and our fabrication procedure. In the experimental results and discussion section, I'll detail the performance metrics, and I'll give you an overview of our key findings. Finally, I will conclude and talk about future directions that we can go with our findings. And now for the background. Compliance and maximum strain are two very important performance metrics of soft actuators. Compliance is needed for when the robot interacts with its environment. If malfunctions occur, rigid actuators can cause a lot of damage to the people and equipment around them. The second metric, maximum strain, obviously affects how much the robot can move. More is better. The picture on the right is just one example of a soft robot. You can notice the biomimicry of its soft fingers. Its fingers are actually driven by pneumatic actuators. Compliant materials also enable robots that better mimic people and animals, as you can see from this figure. Having said that, I would like to introduce a device known as the Twisted String Actuator, which is abbreviated as TSA. The operating mechanism is relatively simple. Some number of strings are fixed to a motor shaft at one end and fixed to a load at the other end. The twisting of the strings makes them shorter, which generates linear actuation. In the literature, TSAs output very high forces and are actually very efficient. Actuation is repeatable for thousands of cycles, and its performance can be estimated relatively well using linear models. Note that the TSA is different from simply a motor with some string wound around a spool. The TSA actually outputs higher forces with lower input torque. The TSA has been applied to a lot of robots. They are especially used in robotic hands and assisted robots. Generally, they are made from highly stiff strings. And so while TSAs have many applications, it would be good if they were more compliant. This would give them more use in soft robots and make them safer for human-robot interaction. And now I'll talk about the motivation for doing this study. By simply replacing TSAs with compliant strings, their maximum strains will actually decrease. For example, our group recently studied self-sensing TSAs, which only achieved less than 10% strain using compliant strings. Perhaps an alternative actuation method, besides only twisting, could be used. For this, the selection of the proper material is crucial. The supercoiled polymer string is an excellent candidate. This long name is abbreviated as SCP. It is created by coiling polymer threads or fibers. Nylon is a common material, and we use it in this study. The SCP is an artificial muscle in itself. The muscle will contract or elongate due to heat. In robotic applications, the SCP has also been utilized to create bending and torsional motions, as you can see in the pictures on the right. Our strategy is to replace the normally stiff strings in TSAs with compliant supercoiled polymer strings. Heating and twisting the string simultaneously increases the compliance and the maximum strain. To quantify the compliance of the actuator, the stiffness of the strings is obtained. To conduct a pair comparison, the TSA is studied in two different cases, without heat and with heat. We study the TSA with two different string thicknesses, 3-ply and 4-ply. The ply number is the amount of threads used to fabricate the string. We study each actuator at low, medium, and high loading as well. Our setup contains, of course, the TSA with the motor at the top and the load at the bottom. An Arduino Mega controlled the motor and input voltages. The SCPs were heated using joule heating, where voltage is applied between each end of the string. A MOSFET and PWM signals regulated the voltage levels to the SCP strings, which directly determined how hot the SCPs were. We use a magnetoresistive position sensor with a 0.14 mm resolution. The analog to digital conversion was 14-bit. Now for our fabrication procedure. You can see the fabrication procedure consists of 4 steps: coiling, heat treatment, twisting, and another additional heat treatment. For heat treatment, pulses are between 7 and 10 seconds long, with 100 seconds of rest in between pulses. The voltage levels in both steps 2 and step 4 were determined experimentally. They depended on the ply number, so the thickness of the actuator, and also the length. It's important to note that the voltage in step 2 is actually greater than the voltage in step 4. This is because the resistance of the actuator in step 2 is actually higher than in step 4. When you twist the SCPs in step 3, the overall structure becomes thicker and shorter. Both of those factors contribute to less electrical resistance. So you need to apply less voltage to compensate for that decrease in resistance, or else your actuator will burn. In all cases, a load is suspended from the actuator. The load was 150 grams for 3-ply actuators and 200 grams for 4-ply actuators. And that is the load in step 1 and step 2. However, in step 3 and 4, the load actually depends on the load that you are running the experiment at. Inputs were monotonically applied from 0 to maximum, then back to 0, as you can see in the figures on the right. The maximum input for both motor rotations and voltage was determined experimentally. Too many motor rotations will actually buckle and break the TSA, whereas too much input voltage will also break it by overheating the actuator. We use 2 metrics to quantify the maximum strain and the normalized stiffness of our proposed TSA. The TSA contraction percentage is given by delta XU. It is dependent on XL and X, where XL is the length of the loaded TSA with no heating and no motor rotations. X is the length of the loaded TSA after either heating or applying motor rotations. The normalized stiffness K has units of newtons. F is the load attached to the actuator. L0 is the unloaded actuator length, and L is the actuator length with a load. Although there is noticeable hysteresis in the length-load relationship, we are able to approximate the normalized stiffness using a linear fit. 4-ply strings, you can see, are stiffer, which makes sense because they are thicker. The next set of results is for the passive string case, where we only twist the strings and don't heat them. Again, there is noticeable hysteresis in this relationship. The average maximum strain was only 17.2% for 3-ply strings. 4-ply strings are not pictured here, but they had similar results. And so on the left is the relationship between length in motor rotations, and on the right is the relationship between length and time. And here you can see the TSA in action. This clip is for 3-ply SCP strings that are not heated. You can see that the motor simply twists the strings to 90 turns and then twists them back down to 0 turns. And this next set of results is for the active string case. On this slide is 3-ply strings, but 4-ply strings had similar results. You can see that at low and medium loading, most strain actually comes from twisting, but at high loading, that is 1.96 newtons or 200 grams, most strain actually comes from heating. The average maximum strain between the different loading conditions was 29.1%, and that is for 3-ply strings. So the graph on the left is where you can see the effects of both motor rotations and voltage. But on the right, you see the effect of only voltage on the TSA. So in this graph on the right, voltages are applied from 0 to maximum and back to 0. You can see that there is some slight noise on that graph, but accounting for this was beyond the scope of the work. Here's another clip of the active case, where you can see the motor twists the strings 90 rotations. After that, voltage is applied in the steps from 0 to maximum, and then again decreased from maximum to 0. After these voltage inputs are applied, the motor simply untwists those 90 turns, and the strings return to their original length. In these graphs, the active strings led to an additional 10 to 12% strain overall. It is interesting that for the graph on the left, strain depends a lot on the loading, that is for the passive case. But for the active case on the right, maximum strain doesn't depend so much on the loading. Overall, active strings with low loading were found to have the most strain. In general, the maximum strain does seem to decrease as load increases. However, the maximum strain will not continue to increase necessarily as the load decreases. There is certainly an optimal load when actuating supercoiled polymers, and that too little load will not cause them to actuate. The compliant TSAs in this study output impressive strains. We characterized the properties of compliant TSAs with different diameters, power inputs, and rotation amounts. These TSAs have promising potential in soft robotic applications, where compliance and high range of motion are necessary. In the future, we want to explore self-sensing for these SCP-based TSAs. We will do this by measuring the change in electrical resistance, as they are heated and as the motor rotates the strings. In the past, we have studied self-sensing in these types of actuators. However, in the past, we only studied the self-sensing properties when they were twisted, but not when they were heated. Another thing we would want to study is the repeatability and lifetime performance of our proposed TSAs. Once we do that, we can compare them to the results in the literature. This concludes my presentation on compliant and large strain twisted string actuators using supercoiled polymers. Thank you so much for listening.